So let's get into this. We're going to have three objectives. The first is to talk about the difference between a point mass and an extended mass, or extended object, which we've alluded to already in the last lesson. And then we're going to calculate torque, and then we're going to define what's called rotational equilibrium and net torque. So let's get right into the first thing here. So by definition, torque is a force that's applied at a given distance from a fixed point, traditionally causing rotation. Now, when we think about this topic, I want you to think about torque being analogous to force. Force is the thing that caused acceleration that was linear, right? If you apply a force upward, if I push on this mouse upward, it's going to lift the mouse up into the air. If I push on it left to right, it will move the object left to right. That's what a force does. A torque does a very similar thing, but instead of causing something to move left to right or up and down, a torque causes it to move either clockwise or counterclockwise. Okay? So just like a force causes linear motion, a torque causes rotational motion. And soon we're going to talk more about, as we've alluded to already, rotational acceleration or angular acceleration. That alpha symbol, that little fish, okay, causing rotation or acceleration. And remember, that was angular acceleration. Okay, and you guys saw it. As soon as I let go, if the balance we had a minute ago wasn't actually balanced, as soon as I let go of one side, the thing would fall, right? And it would start to accelerate in the angular or rotational direction. So again, a torque causes rotation or angular acceleration. Theta is always the angle between the applied force, F, and a line drawn along the direction of the distance r. And the distance r is really the distance between the pivot point. So let's mark this here, please. That's the pivot point, also known as the fulcrum, also known as the axis of rotation. Honestly, any of those phrases are used in any question, so based on what you're reading, if it's an AP test, your homework in your textbook, in the chapter, those words you should be familiar with as being synonymous with each other. So in this case, the fulcrum or the pivot point is at the end of the rod, right? At the end of the rod. And we know that the force applied in this diagram is an applied force at an angle. And this is the applied force acting on this object, and this is the distance from the actual fulcrum. Now, if we were actually analyzing this as a true diagram, we'd also have to indicate wherever the center of mass is. And if this rod is uniformly distributed, then the center of mass would be right at the center, and there would be a second force acting there, mg. But maybe it's not at the center, right? Maybe this has this half of the rod is all metal, and then this part of the rod, maybe this is all made out of wood. Well, if that's the case, then the mass is not going to be directly in the center, or the center of mass will not be directly in the center of the geometric object itself. Okay, but that's not what we're really focusing on too much in this section. More of focusing on if we have applied forces, what happens. Okay, so this would be the scenario we've got here. So keep in mind that theta is that value. Now, help me out real quick. You guys should be good with your math. If I denote this as theta right here, I'm going to pick a value, say 120 degrees. Well, that means that what's left over here is only 60 degrees, right? What is the sine of 60? What is the sine of 60 degrees? Which one is that? Think back to your table, right? What do you got, Christina? Sine of 60. Do you remember that one? It is root 3 over 2. Very good. 0.866 as an approximate decimal. Hey, what's the sine of 120? Jack, Turner? It's the same. So does it matter which angle I actually use here? It really doesn't in the end, because those angles are supplementary. And we know that from our pre-calc course, right, that the sine of an angle and the sine of its supplement are always going to be the same. So the sine of 60 and the sine of 120 are identical to each other. So it really doesn't matter which angle you end up using there. Okay, fun fact for you to think about, because the fact is that we're using sine here. If it were cosine, it would not be the case, right? Keep that in mind, that the cosine of 60 and the cosine of 120 are opposite signs. One of them is 1/2, the other is negative 1/2. So for cosine, it does matter there. So I want to point that out, that it didn't matter which one we use there. Any questions on this idea to start of torque and what it is? So although we used mass to calculate torque earlier, right, when we did that demo there with the fulcrum, we're not really using mass. We're using a force that's applied at a given location. Okay, so let's look at the second slide here. We're going to talk now about what's called the lever arm. The lever arm. And the idea of a lever arm is that we can estimate the distance or the perpendicular distance to the force applied. And as the lever arm gets longer or shorter, we apply more or less torque. So let me demonstrate it. Let me show you first up here. So the formula for torque is, as we know, RF sine theta. But if I rearrange this formula, I can write it like this. F times R sine theta. And I'm going to group R sine theta. So I'm simply just switching F and R, right? Multiplication is commutative, so I can do that. And it's also associative, so I can group it this way. So this right here, okay, is called the lever arm. The value of R sine theta, that is the lever arm. That's why we denoted it up here, okay? Now, what is R sine theta, though? R sine theta is the dotted red line in the diagram. So take a look at these 4 diagrams. Let's start over here, right? There is no dotted red line, but actually, here's the dotted red line in this one. Okay, that's the dotted red line in the first one. And what's happening as we go from this diagram here, by the way, this should be a degrees symbol. I just copied over wrong. I don't know why it's an infinity. Something with the, I don't know, maybe it was a PDF originally. It should be degrees right there. So the length of the dotted red line, notice it gets shorter to here, and then it gets shorter, sorry, it gets even shorter here, and then finally it's the shortest right here. So what's happening is this. If we want to get more out of our torque produced, we want our theta value to be closer to 90 degrees. And take a look at the first diagram. Although we don't see it, there is a right angle. Here's the right angle right there. Okay, on that first diagram, there's a right angle right there. So this angle is 90 degrees. Then this angle next, let's say, is maybe like 70 degrees. Well, if that's 70, then this theta in here is also 70, right? There's that 70 right there. Because those are parallel lines cut by a transversal, the wrench being the transversal. If you need to do this visually, extend your parallel lines, and the wrench cuts through as the transversal. Okay, this angle here is 70, and this angle here is 70. Alternate interior angles. Back to geometry. That's why it was so important that you learn that stuff. Then as we keep going, what will happen is this. Look, the angle gets smaller. This angle now is maybe 50 degrees. Well, this angle becomes 50 degrees. Then here, it's hard to even point it, so I'm going to put an arrow. That angle there is maybe like 20 degrees. The same angle right there. Those are 20-degree angles now. So what's happening is our angle is getting smaller. And because you guys have taken pre-calc and you know your trig functions, have you studied your sine and cosine waves? Have you graphed them before? I think you've done this maybe a unit or two ago, right? You looked at the wave graphs of sine and cosine, how they start and finish. What you'll notice is that sine is an increasing function. If you graph the sine wave, right, that's the sine wave right there. If we were to graph this, this is 90 degrees, this is 180, this is 270, and this is 360. I'm using that instead of pi. I know normally you put like pi over 2, pi, 3 pi over 2, and 2 pi. From 0 to 90 degrees, what happens? Look at the sine function. It's constantly increasing from 0 to 90. Let me use a black dot to show the endpoints. Okay? From 0 to 90, the sine function increases. So the biggest we can get the sine of x to be is when x, or theta, x, you can call this theta, maybe if that makes it easier, call it theta. When theta is 90 degrees is when we get the most out of our sine function. When theta is 0 degrees, we get nothing out of our sine function because the sine of 0 degrees is 0. So the sine function is an increasing function for the domain from 0 to 90 degrees, which is why we're seeing what happens here in this diagram. As theta goes from being large to small at 70, to smaller at 50, to even smaller at 20, we're getting less and less out of our sine function, which means that this quantity up here that I'm circling, this quantity gets smaller and smaller as theta gets smaller and smaller. Okay? As theta gets larger, this quantity, RF sine theta, also gets larger. Now, that lever arm, that concept of a lever arm is really important. So what I want you to notice also again is that the length of that line that's dotted in red is getting shorter. Remember that that red dotted line is representative of r sine theta. Well, r is not changing. R is always the same, right? This is r. Take a look where I'm pointing. This is r from here to here. This is r from here to here. R is never changing. R is the length of the wrench. R is the length of the wrench. R is never changing, but theta is changing, which is why this dotted red line gets shorter and shorter as theta gets smaller and smaller. The dotted red line, look how short it is by the end. So we call this leverage. And if you say you have more leverage, it means you have a longer dotted red line, a longer lever arm. Let's see. Okay, let's move on to the next slide. I'm going to point something out, but I want to wait till we have another diagram. How are we doing on time? Okay, we're doing all right now. So let's just look at the first example to see this. So which of the following hands produces more torque on the bolt shown? So we've got a force of 20 newtons acting at location A, and then we've got a force of 10 newtons acting at location B. Which of these two arms would provide more torque on this object? Well, the first thing we have to start is to recognize what is the angle. What's the theta value in this diagram? It's not given, right? There's nothing shown. So what does it say? Not 0, be careful. The other way around, Seb. Remember, this is my R, and that's my force. 90 degrees. So we call this 90 degrees here, and we say that the angle theta is 90 degrees for both of these. So we know that this is our formula right here, RF sine theta. So this does not matter because the sine of 90 is 1. Okay? That's always the case. Whenever theta is 90 degrees, the sine of theta is 1. So it turns out that when we have a situation where the force applied is perpendicular to the r, right, the distance between them, if they are perpendicular, all we have to do is r times f. We don't need the angle if it's 90 degrees because the sine of 90 is 1. The sine of 90 is 1. So in this scenario now, it's pretty easy. What's the answer? Which of these produces the most torque or more torque on the bolt? Which one is it? Which produces more torque? What are you thinking? I see a couple hands. George or, yeah, go ahead, George. Go with this one. Yeah, they're going to be the same. Okay, so this first one here has a force of 20 newtons at a distance of 1 meter. So that would be 1 meter times 20 newtons, which equals 20. And here's the units, Newton meters. Okay, although this is technically the same unit as a joule, we don't write joules for torque. I know that sounds weird because work, remember work was force times distance, which is Newton times meter. Well, this is also Newton times meter, but for torque you don't write joule. It's not an energy term, okay? It's not an energy term, keep that in mind. Second is the second torque, so we'll call this torque 1. And then torque 2 will be the second length times the second force. And the second length is 2 meters, but the second force is only 10 newtons. So as George said, it is the same value in the end. Okay? Now, if the force acting on the object is not at a perpendicular angle, it's not at 90 degrees, you have to use the angle and involve sine theta. But you could also extend that line and use what's called the lever arm again. So we're going to go back and forth between these two methods of using them. So let's look at our next example to see this a bit better. So example 2 says the following. Find the torque acting on the massless object below. So the object has no mass. Assume it's very, very thin. Or compared to the force, the mass is negligible, we would say. The question is, will it end up moving, and if so, in what direction? So we have to think about the fact that we have torque applied, or we have forces applied at distances which create torque. So we've got two different forces. So here's what I want you to do, please. Take your pen or pencil, whatever you're holding in your hand, okay? Hold it in the middle, please. This works really well. Whenever you're not sure whether the force is going to cause positive or negative torque, I want you to physically do it. So, where you have a force being applied on the side like downward, push downward, and ask yourself which way is it causing your pen or pencil to rotate. So, on the screen I'll show you what I'm doing. So my finger is holding it right here, the red dot, and then I'm pushing down on the right side of the pencil. I'm putting that angle different. The angle doesn't matter right now. But I'm putting a force. I know my video is in reverse of yours, I think. So hold your pencil in front of you, right, like this. Hold your pencil in front of you. And then take your hand and push down on the right side. When you push down on the right side, what type of rotation occurs? What type? Clockwise or counterclockwise? What type of rotation occurs when you push on the right side of the fulcrum? Push down on the right side, I should say, because you could push up and it would change it. So pushing down on the right side, what do you get? What type of rotation? You get clockwise, good. And here's a nice way to see it also, ready? There's the fulcrum. Follow the arrow and kind of like just draw it out like that. See what I just did there? Like it's almost like you're following the direction the arrow is pointing in. So had that arrow been the opposite, let's take a look, please, ready? Had this been a force applied like that, well then follow that arrow and try to loop around the fulcrum. It would have caused the opposite type of rotation. It would have caused counterclockwise. So it's important that we recognize a way to dictate negative and positive torque. Again, if you recall, clockwise we said I despise, and counterclockwise we like. So those are the types of torque we get from the direction it would cause. So this force over here, because it causes clockwise rotation, will generate a negative torque. This force over here, because it causes counterclockwise rotation, that will generate a positive torque. So it's important that we recognize that the forces applied generate either positive or negative torques. So we want to figure out the overall torque. Net means the sum of, right? Anybody know the symbol, by the way? I haven't used the name yet. What is that symbol, the Greek symbol? Has anyone used it before in your other classes? Okay, it's tau, T-A-U. If you want to just jot that down as a side note so you know how to pronounce it if I use the phrase tau. Tau is the symbol used for torque. Okay, it's like a little curled T with a line across the top. So the net torque is the sum of these two torques. Well, let's see. I'm going to call this, let's see, force 1, and I'm going to call this force 2. I know we're getting toward the point where we're running out of time here. Force 1, again, is going to cause it to rotate like this. Right? It's going to cause it to rotate in a counterclockwise fashion, is force 1. So this is going to be a positive torque. And then the other torque generated by force 2, right? Let's put a loop here, will cause it to rotate like that from force 2. So that one is going to be a negative torque. So I put a positive in front of the one that causes counterclockwise. I put a negative in front of the one that causes clockwise. And then I sum these values together. Well, R1 is the distance between the applied force and the fulcrum. That's 4 meters. F1 is the applied force, which is 20 newtons. Theta 1, well, what's theta? Theta is 90 degrees. So this is going to be the sine of 90, so I don't need it. Okay, remember, the sine of 90 is always going to give you a 1 value. That's something that's going to happen a lot in this chapter, so keep that in mind. The second scenario, though, that's at a distance of 3 meters, right? Where is that? Let's point that out. That's this distance right here, 3 meters, right, from the fulcrum to where the force is applied. The angle is now 30 degrees, and the force applied is 15 newtons. Nicely enough, the sine of 30 is 1/2, so we don't really need a calculator to do this part at least. And we can get our net torque. We're going to have 80 here. 3 by 15 is 45. Half of that is 22.5. So let's subtract these. We're going to get, what, 57.5 Newton meters. And notice my answer is positive. My answer is positive. So if my answer is positive, it means that the counterclockwise torque won. That was the stronger torque of the two. If my answer were negative, it would mean that the clockwise torque ended up winning the battle. This is like a tug of war, right? Think about a tug of war, but a rotational tug of war. So because the answer is indeed positive, we know that it will rotate, right? The question is, will it end up moving up here? And if so, in what direction? So the answer is, it will rotate, yes, and it will rotate in the counterclockwise direction. It will rotate in the counterclockwise direction. Okay, we're going to stop there at this point because we have a couple other things to do still, and we'll finish up notes in the next class, and we'll look at a lab. But again, I want you guys to start thinking about the concept of torque and how you need a lever arm or a distance involved. If you want to, you can absolutely start the homework example, and let's talk about this a little bit. It's a bit of a different type of look at an example here. So it says, a wooden square of side length 1 meter is on a horizontal tabletop and is free to rotate about its center axis. And you'll see it looks like a pin there in the center, like a nail. Imagine a nail or a bolt through the center. The square is subject to 2 forces and rotates about the pin that fixes it to the table, as seen in the bird's eye configuration. Find the net torque acting on the object. Now, the reason I put this problem here is to point out that concept of a lever arm. And if you recall from our class last time, we talked about when a force acts, we can use the angle or we can try to make it look like a perpendicular force. So let me put a side example here before we get into this one exactly. Okay, so let's call this the pivot point right here. And let's say that the force acts at this kind of an angle. Okay, we'll call this a force here, and we'll say this is R. What we said, if you recall, was that we could also look at this problem or look at all these problems and say, what is the perpendicular distance to that force being applied? What is the perpendicular distance instead of using the actual distance? So what we can do is we could say that if we were to connect our point of rotation to our force vector in a way that makes it perpendicular, it would look like this. There's the right angle right there, okay? So this is called the lever arm. Some books will call it R perpendicular, as in a lever arm, or the arm that's perpendicular to the force. So what we'll notice is that if I look at this diagram, R perpendicular is absolutely smaller than R. And it might not be obvious, but if you zoom in on it, you can kind of make this into a right triangle, right? This is what R is in the right triangle. This is like the base right here, and this R perpendicular would be the height. So the R perpendicular is smaller than R. The reason for that is, if you recall, what is R perpendicular really? R perpendicular was that R sine theta value. So if we go back, side note, so we know it's not included for this problem really. If we go back and ask ourselves, we said we can use this formula, let me put it down below, we have more room. The torque equals R times F times sine theta. And then if you recall, I said to you guys, well, you know what if we just make it R sine theta times F instead? Well, this quantity here, let me highlight it. This quantity highlighted in, let me use red to correspond to the color, in red is this right here. So think about your math class. You know that cosine of theta and sine of theta, those are always decimals, right? They're always fractions or decimals. They cannot exceed value 1. So in this circumstance, the R sine theta really is a fraction of R. So if R, let's say the value here for this R value was like 10, then maybe this R perpendicular is 8. Or if this were 7, maybe this is 5. But R perpendicular is always going to be a fraction of the actual R value. And you're probably wondering right now, why am I getting into the r perpendicular? Well, it's going to play a role in this problem here. Okay? So let's first start by asking ourselves, if this is the applied point where the force is acting on this corner here and on this corner here, we could figure out this r value right there. And then we'd have to determine that angle also. So theoretically, we could say that this is the rotating axis, so this could be the r value. Get a little bit closer to the corner. Okay, that would be the r value right there. But then what we'd have to do is we'd have to figure out a theta value here. And it's just a lot of work to do that. It doesn't make sense to do this problem that way. To determine r, we'd have to say, all right, each of these sides are 1 meter, right? This is 1 meter, this is 1 meter, etc., around the whole thing. To find r, we'd have to do 0.5 meters squared plus 0.5 meters squared equals r squared, just to get r as the hypotenuse, right? If I'm think about this as a triangle, right? Think about that little triangle right there. R would be the hypotenuse. So we'd have to do 0.5 squared plus 0.5 squared equals r squared just to get r. And then we'd have to figure out theta after that. Now, you guys probably can figure out theta by looking at this. Or maybe, if you think about what kind of triangle we have here. Can anybody see what theta would then be in this problem? What are you thinking, Mauro? Yeah. So this little angle in here would be the 45, right? And then Mauro's saying that this angle over here would be 90. So together, theta would be the sum of those two. So this 45 plus that 90 is 135 as a whole angle. My point is this. The time it just took us to figure that out and to go through this process isn't worth it. So I'd like you to solve this with using the lever arm. So let me explain what I mean by that. So I'm going to erase what's on here now. Okay, I'm going to erase what's on the screen just so you're aware. This is a way we could have done it, but it's not the most efficient manner. Of course, I can't erase a lot of this. Really? Why does this happen? Let me try to see if I can just select and maybe clear. Let's try that. Nice. Not that, no? Okay, perfect. I've never used that feature, sorry. I've always tried to erase and it doesn't work sometimes. Okay, so what we can do instead is we could ask ourselves, what is the perpendicular distance between the rotation point and, again, that force? And if we look back over here, right, see what we did? We extended, the force was applied right here, but we extended the perpendicular distance from the rotating axis right here up to the force arrow, and whenever it made a 90-degree angle. So even though our applied force acted at this location right here, we are extending the length, or the line of action, this is called, the line of action of the force, and we're connecting the r value. So we're going to do the exact same thing now. So watch what I'm going to do. I'm going to take the 8 Newton force, and I'm going to continue to extend it. Imagine it looked like that. Now, when I get to that point, the r value can now be the value between these two. And that r value is r perpendicular. So that distance right there is the perpendicular distance between the force and the actual rotating axis. So what you can do for all of these problems is you could extend your force line of action in either direction. Earlier, we extended it backward, technically. Over here, right? We took this point of action and we extended that line in this direction. And we just put an axis here. And then wherever the r value is perpendicular is the r perpendicular. For example, I'm going to show you what I mean for this one. Like, I could keep extending this way, and I could keep extending it this way. But if I were to try to connect r like this, or like this, or like this, any of these green ones, none of those green arrows, or those green segments, I should say, are perpendicular to the yellow segment. So the only one that is perpendicular to the line of action of the force is the red one right here. So when we extend our line of action for our forces, again, we could extend it this way and forward. But if I were to connect the rotating point to out here, well, that's not perpendicular, that's not perpendicular, that's not perpendicular. It's not perpendicular until you get to right here. And you guys know this from your geometry course. If I recall, I'm trying to think of the theorem. It was with parallel lines and perpendiculars to parallel lines. The shortest distance between any two lines is the perpendicular distance. It was a theorem you went over. And the theorem looks like this. Here's two parallel lines, right? And if I pick a point right here, the shortest distance across is directly across. That's the perpendicular distance versus a trajectory like that or like that. So we are looking at the shortest distance really between the rotating point and the line of action of the force itself. That's what we're trying to find here. So by doing that, we can now say the following. We could say, if you remember, that our torque equals r perpendicular times F. And remember that r perpendicular is really replacing r sine theta. Okay, this, remember here in the bottom, bottom left over here, this is r perpendicular. So we're trying to pretty much get rid of the piece about the angle in these problems. Now, we can do the same thing for the 4 Newton force. I'll use green. We could extend the 4 Newton force until it gets to that point as well. And it's going to have the exact same r perpendicular value, right? They're both meeting at that location in the middle. So even if I extended it this way, nothing is perpendicular except for that dotted blue line. None of those green lines are perpendicular, so none of those will work as r perpendicular. Only the dotted blue line will work. So for both of these problems, r perpendicular is simply 0.5. And I know that because I know that this full length here is 1 meter. Okay? And we were told in the problem that the wooden square has a side length of 1 meter. So that means that the dotted blue line designated as r perpendicular must be 0.5. Now once we know that, the rest of this is easy. It's just take 0.5 and multiply by your force, and you got to do it twice. So again, for total torque or net torque, right, we're trying to find the net torque, we have to add torque 1 and torque 2 together. But one of them is causing a clockwise and one is causing counterclockwise, right? So we have to consider that one of them will be positive and one of them will be negative. So let's start by calling this F1, and let's call this F2. Now, if the 8 Newton force is F1, would that generate a positive or negative torque? And if you're not sure of the answer, think about this question. Would the 8 Newton force generate a counterclockwise or clockwise rotation if it were the only force acting? So again, if the 8 Newton force were the only force acting, would it cause the object to rotate in a clockwise or a counterclockwise direction? Christina, what are you thinking here? Good. So remember how to do this, right? Take your pencil, see the arrow here, and think about pushing on this block. If I push, physically think about it, right? Here's your calculator, because this is a block, maybe, or a phone. Phone. If I were to take this phone and I were to push here, what's it going to do, right? That's what you have to ask yourself. It's fixed in the middle, so my fingers are holding it. Look, when I push in this direction, there's the rotation. When I push in this direction, it's the opposite rotation. That's why one of these will be positive and one of these will be a negative torque in this problem. So yes, F1 will cause a counterclockwise rotation, which is positive. So this remains positive as torque 1. Well, if that's positive, then the other one, it must be negative. Okay, because torque 2 comes from F2, and if F2 is applied to this block, take a look where I'm pointing, right? It's applied right there. The block will then rotate in this direction, which is clockwise, and clockwise is a negative torque. So I'm calling torque 2 a negative quantity because it comes from force 2, which causes clockwise rotation. Okay, and then the next step is to say F1 times r perpendicular minus F2 times r perpendicular. Because r perpendicular is the same, we don't have to call it r1 and r2 here. Do you see what I'm saying? R perpendicular was the same value for both of these forces. So I'm not designating 1 and 2 as subscripts there. And technically speaking, I could factor the r perpendicular out front if I wanted to. But at this point, it just becomes plugging in the numbers. F1 is 8 times 0.5 minus F2, which is 4 times 0.5. And that'll give me the net torque acting on this object. So half of 8 is 4, half of 4 is 2, 4 minus 2 is 2, and my units will be Newton times meter. Okay. So the idea of a perpendicular distance is really important, and it's not obvious all the time. So what did we learn about in this problem? We learned about extending our force along its line of action. Line of action. Okay, so we could always take the force vector and continue to draw it infinitely as far as you want in both directions until you get to the location where you have a perpendicular distance from R that intersects with F. Any questions on this one? We're going to do a second one in a moment that's similar, but it has to do with a rotating circular object, but we're still going to have a perpendicular distance. Okay, let's look at the second one. I think it'll help a little bit too. So the next one, we've got this little pulley system here, and we're told that we have 2 wheels that are fixed together, and they are free to rotate about a frictionless axis through their concentric center. Concentric? Vocab? Geometry? Concentric? What do we got? Concentric, concentric, concentric. Nobody remembers this word? Concentric from last year? Think about it. Think about your root of it. Yeah, Eduardo, go ahead. Good. Very good. So like right here, what Eduardo's talking about, let's put a dot right in that center. Maybe I'll even use red so you can see it better. So there's the center that they're sharing right there, okay? Con, with the same center, okay, if you want to break down your words there. As shown above, or below, I put above, sorry, this should say below. Or just as shown. As shown, 4 forces are exerted tangentially. This is me having typos, sorry, I added this question on the wheels. Do these forces cause the wheel to rotate is the question. Okay, just a general question is yes or no here. Do they cause it to rotate? And we could look at it, right? And just look at the problem without even doing some math. What is your answer just by inspection? What is your answer just by inspection, you think here? What do you got, Jack Turner? Yeah, it's likely going to go clockwise. I agree with Jack. Now, there's 1, 2, 3 forces. These 3, right, are all going to cause it to rotate this way. And this one force here is going to cause it to rotate that way. Now, theoretically, right, had the force in this position been like 5F, then maybe it would have balanced all of these, right? Maybe. But that's, again, a function of the problem. But because this is just F and this is just F, we can see already that these 2 are going to balance each other. Right? They're both at the same location, technically, with respect to the origin, or the axis of rotation, and they're opposite directions. So these 2 forces here are likely going to be forces that do cause it to rotate in a clockwise direction. Now, because we're in a physics class, let's guarantee that. So let's look at our math involved here. What is the distance between the center of a circle and the outer part of a circle called when you're looking at a tangent vector? So what might we call this right here? From geometry again. And it's not just the radius. I know the answer, you think it is like, oh, it's the radius, obviously. I get what you mean. But like, I'm saying whenever an object is tangent to a circle and you connect the radius, what do you know about those 2 segments? From geometry class, what must you know? Justin, what are you thinking? It's always a right angle. Good. And that was, I don't know if it was a theorem or one of the things you guys learned, but whenever you have a point of tangency and the origin connected, it's always going to make a right angle. So the distance here to here, there's our point of contact, has to be at a right angle. Here to these two have to be right angles. And then I'll use red for the last one. This distance here has to be at a right angle. So when it comes to a pulley, write this down. This is really important. When it comes to a pulley, all of the tangent forces from, in this case it would normally be a rope or a cord, are perpendicular to the radius. Okay, and this is for a pulley. And this is an example of a pulley. Imagine a pulley that has a central hub and then an outer hub that are connected to rotate together. Some have ropes hanging on the inner hub, some have ropes hanging on the outer hub. If you've ever done any weightlifting at a gym, you've seen pulleys like this before, where the rope or the cable comes over the top and it lifts the stack of weights. It's the same concept here that you're seeing. So my point is that in all of these calculations we're about to do, we don't have to worry about sine of theta, because theta is 90 degrees for all of these. So the r value that we have located, or namely the radii, are really r perpendiculars in these problems. So I'm going to erase. Can I do it? No, I can't erase, of course not. Let me just try to get rid of that real quick, if that's possible. Okay, perfect. So when we look at these, we want to think about the fact that the distance from the rotating axis to the force in this problem is the radius, really. So we've got this force, both acting on the outer edge, which are at a distance 2r from the center, right? This is the distance 2r that's showing from the center to the outer wall is 2r. So when we look at our net torque, we've got torque 1, we've got torque 2, we've got torque 3, and then I'm going to put minus, well, these will all be, let's see, I'll leave this as positive, and torque 4. Now, if we look at these three, this is going to cause torque 1, this will cause torque 2, this will cause torque 3, and this one will cause torque 4. And if we look at this problem, we can see that torque 1, torque 2, and torque 3 are all, we said, causing clockwise rotation. So I'm going to go ahead and make these all negatives now. The actual net torque is negative. Now, let's write these each down. So from torque 1, it's going to be a force of F at a distance of 2r. Again, let me point that out so you see that this is the force F right here. The distance from the rotating axis is 2r, and because it's causing a clockwise rotation, we put a negative sign in front of it. So in the last problem, by the way, I put negatives up here to make it a little more obvious. So if you want to be consistent and put the negatives in front of your torques to start, and then just carry them down, that's fine. The second torque would be identical to the first torque. I mean, this is the same force, right? Look at these two. These are both a force of F, and they're both at a distance of 2r. So the next one is going to be, again, 2r times F. The third one, well, that's going to be identical also. What's the difference, though? What's the physical difference? The torque generated would be the same as torque 1 and torque 2. But how does torque 3, how is it actually different? There's a small difference you should be able to see here. What do we notice? Francisco, what do you got? Yeah, very good. It switches the R and the F part. So in this case, it would be a single R times 2F, which is the same in the end, right? Let me point that out, what Francisco was just saying. This force right here is double the other forces, but it's only at a distance R from the center. So there's your distance R, which is that. And this is the 2F being pulled, and that's that 2F. But in the end, these are all the same now, right? 2FR is pretty much what they are. And then the last part is this force right here. And this force is at a distance of 2r. It's creating torque 4, which is a positive torque. And that's a distance 2r times F. So what I was saying before is what we notice. this torque 4 could really just cancel with torque 1, right? Take a look at the numbers. That's the same as that. They cancel each other. Or torque 4 cancels with torque 2, or torque 4 cancels with torque 3, actually. Any of them kind of just cancel. But the key is to remember that when those two cancel, what are you left with? This is what you're left with right here, which means that the net torque will be negative. And as I think it was Jack Turner that predicted, it will rotate in the clockwise direction. Okay, the net torque will be negative 4 RF. That's what the net torque will be. So the answer is clockwise, or the answer is yes, really, right? Do they cause the wheel to rotate? The answer is yes, but in the clockwise direction. So when you get to a problem where you have the same force applied at the same distance from the rotating axis, but causing the opposite direction of rotation, you could just, by inspection, cancel those forces with each other right off the bat. Okay, and recognize that the leftover must create some rotation. If the leftover, which leftover I mean this right here, the leftover has the same sign. Right? There's no way these two things can cancel each other because they both have negative signs. It's impossible. Any questions on this one? Again, perpendicular distance used. Okay, perpendicular distance. Let's look at example 5 here. Example 5 says to determine the location where the 10 Newton force should be acting in order to produce rotational equilibrium if the uniform rod's mass is 4 kilograms. So now the rod has mass. If you remember earlier, we looked at a massless rod, so we didn't have to worry about mg. But now it has mass. And then the follow-up question is the rod in a state of force equilibrium? So we're trying to figure out what should the R value be right here, right? What should that distance be for the 10 Newton force? Well, let's just logically look at this. The 10 Newton force is going to cause it to spin clockwise. The weight of the object, since it's on the left of the pivot point, here's the weight, is pulling down from the center mass. The weight of the object will cause counterclockwise. The 25 Newton will cause counterclockwise. And then the 15 Newton here will cause clockwise. So these two, right, this one, let me see if I can use my finger, right, yeah. Yeah, these two are going to cause clockwise rotations. These two are going to cause counterclockwise rotations. So there's a chance that these could be balanced. Well, that's what we're trying to do. We're trying to figure out what should R be to produce, let's underline this, rotational equilibrium. Equilibrium, if you recall, means that the net force equals 0. But that's force equilibrium. If we're looking at rotational equilibrium, we want to look at a problem where the sum of the torques equals 0. Or the net, right? Net means sum of. The net torque equals 0. That's our goal in this problem. So we want our net torque to equal 0. In the last few problems, we were determining the net torque to see then, oh, does this rotate or maybe it doesn't rotate? So we were trying to figure out the net torque. But I can't figure out the net torque because I don't have this R value here. So the question is not about finding the net torque. It's about saying, what is the R that'll cause the net torque to equal 0? Okay, so we have to list what we've got. So let's start by calling these certain things. I'm going to call this F1. I'm going to call this F2. I'm going to call this F3. And I'm going to call this F4. Why am I labeling F1, 2, 3, and 4? Just so that when I label torque 1, torque 2, torque 3, torque 4, I know where they're coming from. Okay, torque 1 associates with F1, etc. So let's say the net torque equals 0, which equals, now we got to go through this process again. Again, F1 causes clockwise rotation, so that's a negative. F2, look at F2. F2 causes counterclockwise rotation, that's a positive. F3 causes counterclockwise, that's a positive. And then finally, F4 causes clockwise rotation, that's a negative. So I know my signs already. Like we just said a moment ago, right? 2 of these were causing clockwise and 2 of these were causing counterclockwise. All right, so let's start writing down what we know as values. So again, the net torque equals 0. We already wrote that, so we can carry down the 0. Torque 1 comes from its distance, R1, put the negative sign in front, times F1 times the sine of its angle. Torque 2 comes from its distance times its force times the sine of its angle. But that angle for torque 2 is what? What is the sine going to reduce to for that one? What can I just do? I can just drop it off? Why? Why can I drop it off here? Jack, what do you think? Yeah, exactly right. So this is just a 1 here, so we don't need that in the problem. It's not 0. Remember, I'm not canceling it. I'm just putting a 1 there to show that R2F2 is all we need for that. Force 3 is positive also. We're going to call that R3 times F3. And then finally, force 4 is the R that we're looking for. So I'm just going to call that R for now, right? Because on the diagram it was called R, and we're looking for it, so I'm going to call it R still. We have force 4, and then the sine of theta 4. And now it becomes a plug and chug. 0 equals, and we could solve this analytically, or algebraically rather. We could isolate R in the equation by moving this over and move this over and move this over. And then we could take this and divide by this whole quantity. So I can do that, but I'm just going to plug in so you guys can see the numbers for now to make it a little simpler. R1, again, is the distance between the pivot point and the applied force. What is R1 in this problem? What is R1 in this problem? Look for F1 and look for the distance. Christina, what are you thinking? Yeah, and again, where is she seeing that? Here's the point where it's applied. Here's the pivot. From here to here is 6 meters, right? We know that from above. That's 6 meters. And then there's another 4 meters right there. So we're summing together this value here plus this value right there. So 10 meters times its force times the sine of 60 degrees. And remember, I could use sine of 60 or I could use sine of 120. It doesn't matter in this problem. We talked about that last class. Then we have R2 next, and R2 is 6 meters. Okay, this is R2 right here, the distance between the pivot point and F2, and then F2 is 25 newtons. Next, F3, its value or distance away, R3 is 2 meters times its force, which is mg. So this is 2 meters. Now, what is mg? Well, the mass was given. The mass is 4 kilograms. So we've got 4 kilograms times 9.8 meters per second squared. There's the mg value. And then finally, the last step is minus. Well, r is unknown for the last part. F4 is 10 newtons. And then we have the sine of 45 degrees. Okay, so our goal pretty much is to solve this equation listed here. Okay, to solve this for little r. Any questions on this idea? I know it's a lot because we saw 4 different forces, some perpendicular, some at an angle. Notice I didn't even write the one for the weight of the object. The weight of the object, because the bar is horizontal, the weight acting down has to be perpendicular. So I didn't even include sine in this one when we did the weight because I knew it was going to be sine of 90 again, so it didn't matter. Okay, let's see what a number comes out to be. Okay, let's see. Thanks for the notice, by the way, Julia. I just saw it now. Thank you. The number will turn out to be for this one 13.9 meters. Okay. Just close this so I can see you guys better. Okay, there we go. 13.9 meters, which actually is somewhat reasonable. According to our diagram, it's not reasonable, right? So what's the assumption that we're making here? That things are not drawn to scale, right? And you see that a lot in textbooks. So the reason it's not drawn to scale, you know that, for standardized tests, is so that you can't just estimate and measure and figure out which choice is closest. That's why diagrams are not drawn to scale in tests, or else you could just use your pencil, right, and figure out which choice looks the best. So 13.9 is, remember, this distance right here. Okay, which if I were to, according to my diagram, this looks like maybe 6 meters. If this is 6 meters right here, it looks like this is probably 6 meters also, but clearly it's not drawn to scale. So that's the distance for R of 13.9 meters. Jack, go ahead. Yeah, that's a great question, Jack. So if you look at this diagram, what we're trying to say here is that the pivot point is just not embedded in the center of the mass. So it'd be like, remember the other day when I had the ruler and I was doing the thing with the ruler like this, and I would move my hand toward the center and it would meet in the center? Imagine if I put a pivot point on this pencil right here. Then most of the weight would be on this side, wouldn't it? And it would cause an imbalance. So the center of mass, it could be on the side of the pivot point and therefore it causes a torque. So in this problem, it just happens to be that the pin is not located at the center of mass. And I'm doing that on purpose here so you can see that happening. Okay? Good question, Jack. So the follow-up question is the rod in a state of force equilibrium? Is it in a state of force equilibrium? We now know it's in rotational equilibrium because that's what our arrangement was. We set the sum of the torques equal to 0. But the question says, is it in force equilibrium? Let's look real quick. And this is an easy one we can do. So in the x direction, what do we have? Well, we've got F1, which is 15 newtons, acting to the right, but it's at an angle of 60 degrees, and since we want the x, we want the cosine of 60. So that's the x component of this guy over here. Then F2, does that have any x component to it? Does F2 have any x component to it? No, I would hope not, right? It's acting straight down. Look at F3. F3 is acting straight down also, so there's no x component to that either. And then F4 is going to be acting in the left direction in this diagram, right? It's pushing back in that direction technically. So that's going to be a minus, and that'll be 10 times the cosine of 45. So that's our x direction sum of the forces. And that number will turn out to be, I had a number for myself here earlier. You gotta be kidding me, where is it? 0.4. So in the x direction, this is almost in a state of equilibrium. The forces acting on this rod are pretty close to being balanced with each other. Okay, if that were 0, we would know it's in a state of equilibrium, the forces at least. Now, in the y direction, though, we've got a lot going on. We've got the 25 Newton force. Well, let me go in order. I'll start with F1 again. I'm going to move my way across, okay? So F1 will be a positive 15 newtons, and that's going to be times the sine of 60, right? That's the y component of that acting up. Then the y component of F2 is the entire thing. F2 is 25 newtons acting down. So that's minus 25 newtons acting down. F3 is another minus, and that's going to be minus the weight of the object. And that weight is 4 kilograms times 9.8 meters per second. That's whatever the weight is, that force. And then finally, F4 is also acting down, right? Look at F4. It's acting left and down. So down means another negative in the y direction. That's going to be a 10 times the sine of 45. So just by looking at the numbers right off the bat, you know that this is not going to be in a balance in the y direction. It will not be in equilibrium in the y direction. And the number turns out to be 58.3. And we're looking at negative because its overall is downward. So these are our numbers right here and right here for the net force acting on this bar. So here's how we would conclude this problem. I know we're a minute over. I'm going to end right with this conclusion. So we would conclude with the following. It is in rotational equilibrium because we set the sum of the torques equal to 0 over here, right? We set the sum of the torques equal to 0, which is what caused rotational equilibrium in the first place. So that is true. Rotational equilibrium exists. But because the net force acting in the y direction is not 0, the x is close to 0. So if this were like 0.4 and this were 0.3, I might say like it's pretty much in equilibrium there. But the y direction is showing you that it's clearly not in a state of equilibrium. There's a net downward force. Now, to finish class, what resists that net downward force? Because this bar is not actually moving, right? It's not moving. So what is resisting the 58.3 Newton force acting on this bar in the downward direction? What physically is resisting it in this diagram? Physically. Seb, did I see your hand pop up just there? No? He's like, no, that was not me. Okay. Come on, look at the diagram. Go ahead, Jack Janisi, tell me. Yeah, it's the nail or the pin, whatever that was. And we say, I use the word pin all the time. So whatever that structure is right there in the center that's holding this in place is the piece that's resisting vertical motion. So likely, and if you do this, you'll know, if you take like a pencil, right, hold it with your hand like that, take your other hand like this and pull down on it. And I do it in class all the time with a wooden pencil. If you put enough force downward and you hold this hand steady, it'll snap. It'll do what's called shearing. We'll learn more about that next year, and if you take the engineering course, it's shear stress. Shearing occurs a lot. When a bolt connects several members together and there's too much force on it, it'll literally just snap in place. So if you want to try that with a wooden pencil, just hold this steady and pull down on the other end. And that's what would happen to this pin if its maximum strength were less than 58.3. But likely, if this pin is made out of aluminum or even like something stronger like steel, it's not going to crack under a force of 58.3 newtons. Okay, so if its yield strength is the phrase there, if its yield strength is more than 58.3, this object will not fail. It will not collapse to the ground or wherever it is. All right, so what we're going to do is next class, I'll see you guys next week. Next class, we'll take... All right, example 6. Write the equations needed to produce linear and rotational equilibrium for the uniform rod shown. So we're taking a look at this example here, and we're seeing that we've got 3 different forces acting. One of them is the weight, and 2 of them are external applied forces. And they're acting at distances d1, d3, and then it looks like F2, right, this guy here, is at a distance of d1 plus d2. So let's figure out what's going on. So the first thing we have to ask ourselves again is, what kind of torque do these forces cause? Do they cause clockwise or counterclockwise? So this force here would cause, if we continue the direction, right, continue the direction around the pivot, this would be a counterclockwise torque from F2. F3 would also cause a counterclockwise torque. The weight, though, itself would cause a clockwise torque. So let's start with the equations needed to produce rotational equilibrium, then we'll get into linear equilibrium. So we're looking at some of the torques and some of the forces. So we have to know that the net torque must be 0 for it to be in rotational equilibrium. And then what we're going to do next is we're going to say that the net force has to equal 0 for it to be in linear equilibrium. So let's analyze these separately. So again, we've got, thinking about our torques as negative and positive, we've got F2, we've got F3, and we've got the weight. So when I look at this one, this will cause a counterclockwise torque, this will cause a counterclockwise torque, and this will cause a clockwise torque. That's how we're going to approach this as always. So counterclockwise, we're considering positive for torques. So we've got positive for torque 3, we've got a positive for torque 2, and then we've got a negative for the torque due to the weight. We'll call that torque 1. Okay, and that's going to be equal to 0. So again, they're calling this the torque generated by the weight, torque 1. Torque 3 in this problem is caused by F3, and that's at a distance of d3 from the pivot. So here's the pivot. This is the distance d3 caused by F3 at an angle beta. So we know that this is going to be d3 times F3 times the sine of beta. Then we look at torque 2, and torque 2 comes from F2. This is causing a counterclockwise again, so another positive sign here. And then what we know is that, well, the angle now is theta instead of beta, the force is F2, and the distance from the axis of rotation to the force is d1 plus d2. So this is going to be d1 plus d2 as our distance times F2 times the sine of theta. And then last but not least, we've got torque 1 caused by the weight. And that's going to be at a distance d1 from the pivot point. And that's right here. There's the pivot point, there's the weight. And we know that when a rod or an object is horizontal, its weight pulling down will be at a 90-degree angle. Okay, so this angle is 90 here. So we're going to have a minus again because it's clockwise here. Again, these other ones were plus. This is a minus. The distance is d1. The force acting down is the weight, which is really just mg, and then it's times the sine of 90, which is 1. So that's our equation for net torque. Okay, again, this is the equation for net torque, and that net torque is set equal to 0 to show that we're in rotational equilibrium. Next, we have to look at the net forces acting, and net forces are the easier portion because net forces are from, Newton's laws from earlier this year. We have to think about the net force acting in the x and the y direction, right? F net in the y equals 0, and then we'll do F net in the x equals 0. So in the y direction, we've got 3 forces acting. All 3 of them act in the y direction. Now, components, obviously. And I'm going to draw the components, right? F3, its vertical component is that. F2's vertical component is this. And then F1, the entire thing, is the vertical component. So those 3 green arrows are showing the vertical force vectors. So we've got, in the y direction, F3, but that's going to be a negative because it's acting down. And then it's going to be times the sine of the angle, which in this case is called beta. Again, sine for the y direction, cosine for the x direction here. What else in the y direction? We've got mg acting straight down. That's a force in itself. And then I could put times the sine of 90, but that's just 1. And then I've got a positive force acting from F2. And that's going to be F2 times the sine of its angle, which is called theta. And that equals 0. Okay, and that equals 0. And that's my equation in the y direction. Then we've got to take a look at the x direction. And let's use yellow, we'll use yellow for the x. This F3 has a small component of it in the x. F2 has a small component in the x. And the weight has no component in the x because it acts straight down. So the F net in the x direction only involves forces 3 and 2. Now, since force 3 is to the right, we're going to consider that a positive in the x. And since this is to the left, that's a negative in the x. So in this case, we would have F3 acting to the right times the cosine of its angle, which is beta, minus F2 acting to the left times the sine of its angle, which we've denoted as theta. And that will equal 0. And this is the equation for linear equilibrium in the x direction. So again, we've got rotational equilibrium here, where the net torque equals 0. We've got linear equilibrium in the y direction here, where the net force in the y direction equals 0. We've got linear equilibrium in the x direction, where the net force in the x direction equals 0. And if these 3 things happen, we would say that this member is in what's called static equilibrium. It's neither rotating nor translating. Static equilibrium.